Okay, so do you have your book with you today?
Hold
That's okay, Ted. You will listen carefully and make good notes.
on.
Good. Okay. So last class, what did we do? Last class, what were we looking at? The materials, yeah. We did the different structures, different bondings, yeah. What was our bonding we had? Ionic, covalent, metallic and van der Waals.
Yeah. And we take the shape that's a crystal or center cube.
Yes, that's it,
and
that's
we
it.
got the
Yeah, that's it, yeah. Now, let's see, next section, we're still staying thermal properties perhaps, is that what we're doing now? Yes. So who has their book? You have it? Why not? Who has their book? Leslie, no book?
I left the book, sorry.
Oh.
Good listeners.
You listen carefully. Where's your notebook? Well, come on, take it out.
Okay.
You have the book?
No.
Why? Why not? So who actually has the book? 2 people. Great. He lives here. Of course he can always have it. It's going to be in his room. Now please don't, you can have that, but please don't spill it, because if you put it on the floor, maybe you'll knock it with your foot. So, I don't know, maybe it's safer to put it on this. Hey.
Your class for a second.
Oh, yeah, that's fine, yeah, what do you want to enlighten them about?
2 things.
Yes. Okay, everybody listen, please.
Okay, so the first thing is I was talking to my group, my tutor group today, and some of you don't realise that your independent learning notes are on the EAP Moodle. Okay, you know the way you have to do learning logs and you need to fill in needs analysis sheets? Yeah, and you need to fill in reflection sheets. Do you remember when Stephen was going through this with you? Okay, well...
We did this a while ago though. Yeah, but so you're saying your group didn't know that it was on the EAP page. Does everybody here use the EAP page on Moodle? No. This is perhaps a bad idea. If you look at EAP Moodle, Lorraine is saying that you'll have all your documents there for the learning log, which is due probably in 2 weeks, isn't it?
Yeah, around the 20-something of December, 21st of December.
In the group tutorial this week, we're going to spend some time on looking at examples of learning log, independent learning in the learning logs.
Yeah.
You all remember me telling you about learning logs, right?
No.
But you started late.
So I don't.
Okay. Right. You said there was something else too.
Yeah. The end of year party. It's a party that we hold every year for the students. It's not a religious party, but it is one that we all get to kind of chill out. You get to sing. I think Stephen, you sang last year.
Don't quite remember that.
I remember you singing last year.
I wouldn't exactly call it singing though.
It
Talking
was
with
more than
talking with a rhythm, perhaps.
Ergo singing.
Did you rap?
And
I'll think about it for this year, actually.
and there was food, and the students got up and did karaoke, particularly the Chinese students, and there was a magician. One of the students was a magician. There was what else was there last year?
Mostly some of the students were singing, and some of the students did magic. And then
there was a guitar. So I was saying you could bring in your guitar.
Who was it that solved the Rubik's Cube like really quickly?
Yeah.
Who was that?
On the stage.
Do you all know that?
One of the students, do you know the Rubik's Cube?
You know that game where you turn it to make all the
The
colours?
squares.
Oh, yeah, yeah.
There was one student able to do it in 10 seconds.
10 seconds or
Oh
something.
my god.
Done. Huh? Maybe so. It was
So
a bad dip, wasn't
If
it?
you have, I've no idea, I
I
can't
think it
remember.
was, yeah.
If you have a special talent,
Yes.
yeah, that doesn't cause anything to explode or people to get hurt, and you want to show it. Another student did a poem in a different language.
Oh
In a
yeah.
science fiction language.
Oh yes. Does anybody here know Klingon?
No good.
You know Star Trek?
Yeah.
Do you know Klingons?
I don't know English,
Klingons are a
so-
species on Star Trek. It's a
The
TV
warrior
show.
species.
Okay.
You
He
lost
sang, oh, it's
interest
a warrior
already.
song. He sang it.
That was it, the warrior song in Klingon.
So everything
Yes.
and everything goes. So basically,
Crazy.
yeah,
Yes.
kind of crazy.
So anyways, when is that one now?
That's Friday the 14th. It's
Next week.
um,
Friday
it's,
plus
yeah,
2
it's not
weeks.
this Friday. It's the following Friday.
Okay.
And it's in the canton
After the exams?
before the exams.
Yeah, it'll be after your
Next
speaking
week.
exams though. Next week on
Yeah,
Friday.
Next Friday. Oh, and one more thing. We did a little kind of students get each other a little gift, just a cheap little gift for about €5, and you put it into a bag, and then everybody can take out a gift, and everybody has a gift from everybody else. Okay?
Lovely.
All right. So there you go.
Grant, thanks.
Okay.
Okay, any questions about that?
Yeah, about the first one you talked about.
What's longer?
Did you sing?
Like I said, I wouldn't call it singing. And I won't do it again anyways.
You have to do it this year.
I don't have to do anything.
Okay, and what you want, the first thing,
Hmm?
the first thing, what you
So the
need-
learning log.
Yeah.
It's part of math. Log.
Oh my goodness. You know, it's funny, this is recording because I was about to start. So when you watch this video later, you'll just get a repeat of all this. Do you do you remember me doing the group tutorial about the learning log? Do you remember this? Like
The paper that you
the
get out.
paper, and you have to write down what English you need to improve.
Oh. It's very similar.
It's the same. Has anybody made their learning log? Oh my goodness. Okay. This Friday we'll look at examples of learning log. Who's your English teacher?
John.
John and Connor.
And have they talked about learning logs before?
No.
No,
Are you sure?
I haven't seen. I haven't heard about it.
You haven't heard about it. Have they talked about learning logs, Albert?
Yeah, long time ago.
Well, it's due in like 2 weeks, so you need to make it.
And what's
Just
the-
fill that paper and give it to you or what?
No. The learning.
how much?
The
would
learning
that-
log, what is it, like 10% of your grade or something in EAP? Something like this, isn't it? Or is it 5%? I can't remember off the top of my head right now because I'm having a nervous breakdown. The learning log, you have to say what areas of English you need to improve, and then you have to... Leslie, you know about the learning log because you were saying you want to improve your speaking
You
Yeah.
sing.
and you were recording the conversation. So that's an example of Leslie doing something to improve a weak area of his English, and he's going to put this in his learning log. So Albert, what was your weak area of English?
No week.
Okay, so you need to do something where you can show improvements of your speaking.
And how do
English
I
teacher.
use?
Well, look, he recorded this
Yeah,
conversation
I've recorded conversation with
with Albert.
Albert, so that can be belong to me and belong to him too.
Sure.
Yeah.
Okay. But
I am weak in writing, so.
so you need to do something to improve your writing. Look, my advice is this. You can ask your English teacher. So you can ask Colin, look, what can I do to improve my writing? He would say, I don't know, try doing this. You can do it, and then you can put that in your learning log, and there you go.
That's it.
Well, you have to put a form on the top saying, like, this is my exercise to improve my writing, and then at the back, when you finish it, you have to say how it helped you, basically. 500 words, that's right, Albert. Yeah, you see, you remember. I told you about this. Yes?
Yes, I remember.
Great. So we're all clear and we all remember, yes?
It's there.
And we all need to look at EAP on Moodle to download the forms.
when?
You can do it tonight.
Oh my god.
Yeah.
What's the deadline?
What, like
2 weeks.
2 weeks basically.
22nd.
I'm going to start physics now, okay?
Okay. Which page?
61.
61.
62. Okay. Now. Thermal physics. Okay. Yeah. Now, well, does anybody know the word thermal?
Is it temperature?
Yeah, it's like temperature. Very good. Okay, so what unit do we use to measure temperature?
Kelvin.
Celsius is one. Celsius. Now, what's special about using Celsius?
That's Kelvin minus Celsius.
No. What's useful about Celsius? Well, Celsius is used because what happens at 0 Celsius?
That's gonna be
The water, yeah, freeze
Yeah.
for water. And then what happens at 100?
And it's gonna be
It boils. Yeah, into gas. Into steam. Okay? And in between 0 and 100, it's just water, it's just a liquid.
Yeah.
That's Celsius. Now, let's see. They don't do it here in the book, but I want to do it for you. And I think maybe they do it later, I hope. No, they don't. Okay. Let me show you. Okay. Let's see. Now, here's a graph here. Here is temperature and here is volume. What's the unit for temperature?
Students.
Celsius. And what's the unit for volume? Meter cubed. Now, what I have here in my experiment, I'll just make it very simple. I have a box, and it has a gas in it,
Okay.
and I measure the temperature. But I'm able to change the temperature. So I can make it hotter or I can make it colder. Okay. Now, actually, I shouldn't say put in a box. I put it in something that can change its shape.
Balloon.
Yeah, a balloon. That's what I was thinking. Just let's just make it nice and simple. We remember balloon from last time?
Yeah.
So there's the gas inside it. Now what I notice is if I make this hotter, what happens to the gas?
Becomes bigger.
Bigger. And if I make it colder,
Smaller.
smaller. So the graph would look something roughly like this.
Okay.
So maybe let's say for example here is 20 Celsius and here's the volume. Now what you notice is, well, if I make it colder and colder and colder, the volume will get smaller and smaller and smaller. But the volume can never be negative.
Yeah.
So there's a place here where it has to stop. And does anybody know this temperature here?
Minus 100.
I think it's minus 273, possibly.
That's Kelvin.
Yes, that's it. Now, is there a 0.1 in there or not?
But
I think we just used 273.
yeah.
Yeah. Okay, 273. Now, I think the first person perhaps was Boyle, maybe, that noticed this, but the scale is called Kelvin. What you do now is you say, okay, I'll use a new temperature and I'll call it Kelvin. And I'll make it very, Kelvin.
Kelvin equal the temperature minus Celsius minus the temperature.
Basically, Kelvin, yeah. 0 Kelvin equals minus 273 Celsius.
Yeah, that's
And then 273 Kelvin equals
it.
0 Celsius. So today, for example, what's the temperature going to be like? Maybe 280 Kelvin.
Why you need to take?
Today.
Ah,
Today's
in the air,
temperature,
okay.
yeah. Okay?
It's gonna be nearly on the also 273. Yeah, gonna be nearly.
Yeah, about 280, we'll say. So then if you're in a very hot country, the temperature maybe is 300 Kelvin? Yeah, 300 Kelvin?
Oh,
Yeah.
Yeah.
but in our country gonna be more.
Or maybe more, yeah, exactly.
54.
Oh, I don't think it's
Yeah,
4.
really, but in the summer the degrees, the Celsius degree is gonna reach 50 something.
50, so then that would be about 325.
I told you 300 something.
I thought you said 400.
No, I said
That'd be a
300.
problem for you. Okay, so that's Kelvin basically. Now, that's Kelvin is much better to use than Celsius.
Yeah, easy to calculate.
It's easier to calculate. It's always positive. So I think for our experiments, Kelvin will be better to use. Now you can use Celsius, that's fine, but Kelvin I think will be better.
Yeah.
Okay, now.
Even chemistry we use Kelvin.
Use Kelvin in chemistry. Good. Okay. Now, what will we do next? Okay, so now, how do you measure temperature?
Use the Torah.
Use a what?
There's
Ah.
a
Thermometer.
yes.
Now, you all know this. You see it with the doctor when you're sick.
Mm.
It's like this shape.
Ah, you mean the. Okay.
And then there's a liquid inside it.
Oh, but now there's new things.
Oh, I know there's new ones. This is old-fashioned one. And then you have the units here.
It's called zinc.
I think this
is it
mercury, perhaps.
Mercury, yeah.
How do you say the liquid inside the temperature?
This?
What's the name of the liquid?
Wait, I was just about to say it. He was saying it. Mercury.
Mercury.
Yeah, have you done this in chemistry?
It's called toxic.
Oh yeah, it's toxic. Yeah, it is. Yeah,
What's mercury?
mercury. Have you not done mercury in chemistry?
No.
It's a liquid, but it's a metal.
Can burn.
No, no. It's a very very heavy liquid metal. I mean, I remember in physics class in high school, our teacher had some mercury and he spilt it.
Oh my
It fell on the table. But I remember the sound when it falls on the table. Even though it's a liquid, it sounds like balls running on the table. And when it falls off the table, it sounds like you drop a ball. It's so heavy, it just goes dunk, 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 dunk. Doesn't sound like water.
It's poisonous.
It is poisonous. That's why the teacher was not happy when he did this.
Yes, also.
What's this pointless?
This is poisonous.
What's me?
It's harmful for you.
Yes.
That too heavy, expensive you mean?
No, unhealthy. Toxic.
It can make people die.
Yes, it can. Yes?
It's the one on Terminator 2.
Yeah, it's the one in this. Mercury is inside this. Now what happens is when it gets hotter, it goes up,
Higher.
Goes up.
and then colder, it goes down. But the range here, it's only going to be something like, 10 to 30 maybe. It's going to be a small range. Let's see what they have in the picture here. Well, for a mercury thermometer, yeah. If you want more of a range, you'd need like a digital one or something. Anyways, the point is, this is a very old way to measure temperature. Not very good. We'll look at other ways. Okay. Did you write these words down? Thermometer and mercury. And the scale is here. So Ted, what is the name of this? Thank you, Calvin. And Xingdong, what's the name of this?
C.
Flashing dawn, come on, what's it called?
Hell.
Celsius.
Ah, yes, Celsius.
Celsius, yes, of course.
What's the American temperature?
Oh, we will not use that. Fahrenheit.
Fahrenheit.
Oh, we will not use this. It's very bad.
Oh.
Very, very bad.
Yeah.
So we come to calculate.
Huh?
We have to calculate.
Oh yeah, it's terrible, terrible. Don't use that.
Americans use it, yeah?
Oh, yeah, that doesn't mean it's not terrible.
No,
Yeah.
no, I just.
Oh, they do, yeah. Like they're like the only country, or maybe like them and some other small country that nobody knows about that uses it. Yeah, you're right. Strange. Everyone else uses Celsius. Anyways, continuing now. So that's one way to measure it. Second way to measure temperature is what's called, you can see there on page 63, constant volume thermometer. Constant volume gas thermometer. So that's one way. Second way. Okay.
What's that constant volume gas?
Thermometer.
Yeah.
Okay. Now, there's a picture here for you. I'll try and draw it here. If I get my picture good.
You mean like in a water pump?
Come on, Mustafa. Now, what's wrong, Mustafa?
No, we're discussing this. No, we're not discussing anything. You're an idiot. I'm not discussing anything.
Come on, come on. Now here, this is the gas thermometer. Here is mercury. That's mercury, okay? And then here is a gas. Now if you think back to our hydrostatics, what can you say about the pressure here?
Gonna be high.
Say.
The same. The pressure here is the same as the pressure here. Yes?
Yeah.
Now, if this was to get hotter, what happens to the gas?
The gas will pour the liquid.
It gets bigger, which means there's more pressure here.
Yeah.
So that means there needs to be
Go up.
more pressure here, which means there must be more mercury here. So it ends up rising.
Yeah.
So you can use the height measurement here to calculate temperature changes here. So let's have a look. So in this one here, they use hydrogen, helium, or nitrogen. So let's, for example, I don't know, let's use hydrogen. Okay. Yeah, that's really the idea here. Okay. I suppose what you could do if you were committed. What was the formula for pressure? Pressure equals rho GH, isn't that it?
Yeah.
Now we know G, yes?
Yeah.
We know H because we can measure it. We know rho because it's mercury, so we can just look it up.
Yeah.
So we know this. So together with these three, we can know the pressure here. Yes? Which means we can know the pressure here. Yes? Which means we know the pressure that this gas is at. So actually another way you could use this thermometer is to measure pressure. Do we have the density of mercury? Did we do that last time? No, we didn't. No. But anyways, if I knew the density, I could find the height and then I could know the pressure, so I know the pressure here. So the pressure here is the same as the pressure here, so I know the pressure that the gas is at. It's another way to do it. Another thing you can use it for. Yeah?
So we'll kind of find from the same formula. I mean, to gas, we're gonna apply the same formula to gas, like on the other side.
Oh, for pressure, yeah.
Yeah. So
yeah.
like kind of finding rho of the gas, something like that.
Oh, I see what you mean. So like here you have, now actually, yeah, okay. I suppose what's a little bit unfortunate about this diagram is there's this piece underneath this and so forth. Maybe I should put this container up here to make it clearer. But anyways, I get the point you're making. On the other side you have pressure equals rho GH. But the height here would be this, I think. It's not going to be the same as this. You know, this
How
could
you
be
gonna
up high.
find the height?
This would be the height.
How you will know?
Well, it's how far down it is from the top.
Yeah.
So pressure equals rho GH. Now, you know the P from this side.
Okay.
You know, maybe you don't know the density. But you know the G and you know the H.
Yeah.
The H, he will give you the H?
Yes.
Yeah.
Yes.
No, what we're doing is, yeah.
Legions.
You mean the
Mhm.
voltage is equal?
We know H.
Yeah, yeah. So we could calculate the rho.
Rho.
Yeah, yeah.
You mean the pressure and the H are equal for the voltage and
Oh, the pressure's equal for both, yeah.
and even height?
Yeah.
No, height might not be equal because this mercury could be up very high.
How you will know the height?
You measure it.
He will give you.
Well, if you need it, they'll give it to you. But for an experiment, you measure it. Okay. Now, another type of thermometer.
And what is this in this? Theta over 100 equal d theta minus.
Yeah. That's if you want to. We'll talk about that in a minute. Is if you want to make a new sort of measurement scale. But we'll do that after I discuss the types of thermometers. So the next one now, this is number 3. Platinum. Resistance. Oh, jeepers.
Mr. Steven,
Yes?
can I stand up? I feel very sleepy.
Well, go get some coffee.
I've drink, but it don't work.
You had coffee today?
Yeah.
When?
Morning.
Oh man.
Yeah, go get another cup of coffee if you're sleepy. Yeah?
I guess coffee has an effect maximum 45 minutes.
Yeah. Do you want to go to the canteen and get coffee?
Sometimes I can't drink too much
Why not? What happened? You explode?
because when I drink too much, I will feel very fatigued.
Well, then
Yeah,
drink
what-
some water.
Yeah.
You'll go to the toilet.
What do you want to do?
Stand up.
Okay, that's fine. That's fine. Try not to fall asleep standing up though. Okay. Now, have you done platinum with Lorraine? Probably not.
To what?
Platinum.
No.
Well, what's very nice about platinum, do they have a picture now for you?
It's
How do you do?
It's expensive.
Oh
metal.
yes, it's very expensive. Yes. So they have a diagram here. But anyways, what they're saying is the electrical resistance of pure platinum wire increases with temperature. Now, I don't want to talk too much about this because we haven't done electricity yet. But what they're just saying here is, for example, here's your platinum. And maybe here's a battery. And the power goes in, and then the current goes in, and the current comes out. And what happens is, if this is hot, it means there's lots of resistance. You know what I mean by resistance?
Yeah.
So the current here will get smaller here. So the hotter this is, the less current you'll have here. And this is actually an example of what's called Ohm's law. Ohm's law. But again, this is something we'll do later, and I don't want to spend time on it now. We'll do it when we do electricity. But just to say it, that's all.
You already asked in the exam.
For what?
This.
Which this?
Yes.
No. This is just me giving you examples of how you can measure temperature.
No, he mean what type of question will come up about this?
No, no, I'm just giving you some background work to start the topic
So we
today.
don't need to remember them.
Remember what? I've not given you a lot to remember so far.
Also, was it vehicles?
No, no, don't you? Yeah, yeah, we'll do that later. But that's the one that
No, no, just stuck in my mind, that's fine.
resistance and current.
Yeah, it comes to,
They're inverse. What's it? They're inversely proportional. So if you, no, they're proportional. If you increase the current, you increase the resistance.
no. If you're talking about the same voltage,
Yeah.
one has
The
to
other
be-
one is if you increase the voltage, you decrease the resistance.
which means you increase the current as well.
Yes.
So current and resistance is
In
the opposite ways.
invertly proportional.
Yeah.
Yes. Increase, keeping the same voltage, of course.
Yeah.
Yes, that's right.
Okay.
But we'll do that. Well, that's actually one of the experiments we'll do in DIT.
Great.
So we'll look at that later. All right, the other one now. Next one. What's this, number 4?
Yeah.
Oh, I can't reach. Thermistor thermometer. And what happens here, again, it's like the last one. Again, you pass the current, and when there's... Here, I'll draw it for you. Like, for example, the picture they have here. Here's some water, and then here's some flame. And then you have your thermometer here, for example, and then you have your thermistor here, and then you have a cable, and then you have a cable, whoops, and then you have your measurement here. So you pass the current through here, and it goes through this, and goes along here. What happens, it's like with the platinum. As this gets hotter, what happens to the resistance here?
It's harder.
It gets, yeah, more difficult. But again, I'll skip this now because we'll do this later when we do electricity.
When we're gonna do electricity?
Electricity will be our next topic after heat. Okay.
May I know you what in the exam till what topic are we responsible for?
Everything they've done so far. Yeah, no, it is actually, just to say earlier, Mustafa, it is actually 273.15.
It's coming.
Yeah.
As the beginning of it, yeah. Okay. There's other thermometers here, but not necessary for our purposes, I think. What I should also say now is the formula. Okay. So let's have a look here. Did you write this down? Or
Yeah.
Okay. Now the formula, theta over 100 equals x theta minus x 0 over x 100 minus x 0.
It's X100 anyway.
Yeah, well, Mustafa, I just wrote it. You have to give me a chance to explain it. You can't ask me when I'm in the middle of writing it. Yes?
Let me understand.
Leslie? I-
X0?
Yes, x 0.
Oh, okay.
In the first grade.
What?
It's like a child in the first grade.
No, don't give him too much credit. More like kindergarten. Right. The values, you can see it on the bottom of page 62. The values x100 and x0 of the temperature measuring property are found at steam and ice melting points, given the fundamental interval of the scale. So look, if x theta is the value of the property at some other temperature, theta, which we wish to know the value of theta in Celsius given by the following equation. So, basically, you can use this formula to make your own thermometer. So do you remember the example I did now for example, let's take the gas one again. And then you have the mercury like this. Okay? Now, what you do first is the x0 is when you put ice here. So you put ice here. Okay? And what will happen, it'll get cold and then this will fall. So let's, for example, let's just call this 0 here. So the height when it's for ice is called x0. Okay? And then you put some boiling water here.
Freeze.
And what will happen? It'll go up.
Yeah.
And that height is called x100.
So you want the height between x and 1000?
No. You just want this first and this first.
Okay.
Then what you do is you put something else. And this is the thing you want to know the temperature for. And you measure the height and you call that x theta. Yes? If you want to calculate the temperature, you can use this formula. So, for example, let's say x0 equals 1 centimeter. And let's say x100 equals 5 centimeters. And then I put my object on it, and let's say x theta equals 2 centimeters. And I want to know the temperature. So it's theta over 100 equals x theta minus x0 over x100 minus x0. Yeah. So that equals 1 over 4. So then I get theta equals 25 Celsius. Because the
right?
Yeah. So this formula is used when you want to make your own thermometer and find out what the temperature is for something on it. Do you know what I mean?
There you go.
So you definitely need this. It's very, very important. Yeah, like kindergarten.
You said it like Jones.
Kindergarten?
Kindergarten.
I'm actually not feeling too well today, so you're probably hearing my cold or something.
Yeah.
Okay, can you go down now?
Okay. To my example.
Yeah.
I'm sorry my picture's so ugly.
No,
For the exam, you must draw a beautiful one.
we have to draw from that.
Yes.
This one.
You want me to go down?
No, we have to draw this picture.
No, you could draw any picture, whatever they ask you for.
Have you written our exam already?
Yep.
Yeah.
Mm,
Would you like Turkish delight? Do you like Turkish delight?
don't really like it so much, actually.
What else? Let me think.
You know what I like.
Coffee.
I'm a very simple man. Simple man with simple needs. Okay, continue.
No, wait, just
What's wrong, Jing Dong?
just spend some minutes to deeply understand.
Deeply understand it. Okay, please go ahead and deeply understand
So
it.
they will give us the x0 and what's x100 and that.
Yeah. Oh, yeah.
And we have to
Or if we do an experiment, you find it yourself. The 4 experiments are Newton's second law, Ohm's law, specific heat capacity, which I'm doing today, next, and wavelength of sodium, sodium light. Yep. Leslie,
Yeah.
is he writing English or Chinese there?
English. English.
Are you sure?
Yeah, I'm sure.
Because he's writing very quickly, which makes me worried that it's Chinese. Oh, Jing Dong! Jing Dong! Get rid of this! Get
Yes,
rid of
okay.
this! I told you I don't want China. Now, I want, look, Jing Dong, I told you before I don't want Chinese in your book.
No, but
I don't care!
okay.
Get rid of this.
Mr. Stephen.
Wait, I'm angry at Jing Dong.
No, Anthony.
I'm angry at you. Do you want me to be angry at you?
No, I will go back to Anthony.
Okay, thank you. I want these deleted also. All gone.
Okay.
Don't want to see it. Don't want any Chinese in this book, okay?
Yes.
Just English. Right.
Yeah, you're taught in German.
What?
Chinese.
Now, can I go to the next page?
Yes, you
Okay.
Either Stephen.
Yes.
Imperial any pressure in the big base.
Here, yeah?
Yeah. It's like the place where a baby, how do you say that? A baby, in a,
No, I don't think it has anything to do with this.
yeah, but, I mean, if something there,
Yeah?
which can grow naturally,
Yeah?
if, with pressure
Yeah?
inside it,
Yeah?
that will come out of here one day.
Yeah?
Yeah,
What's the word for this? Well, maybe you're thinking of this word, expand.
expand.
Maybe.
Yeah.
Maybe it's this word.
When I say it, I think it's like the shape of a lady when he
Oh, you want the name of the shape?
when she is practicing.
Yes.
Yeah.
Yeah?
How do you say that?
I don't know what you're asking me.
Because the shape, I think the season
Yeah?
of this is very similar to a baby was born.
I'm
from
sorry.
this mom.
I have no idea what you're talking about.
I think he's making a statement there.
I mean, when a baby
Yes?
was gonna born, is gonna born
Yes?
before
Yes?
he's born,
Yes?
he's staying in his
Yes?
uh,
Oh, you want the name of this part?
yeah,
Okay, but you think... Alright. Womb, isn't it?
yeah, womb.
Yeah, but what has that got to do with this?
Yeah, in womb, there's some pressure in womb.
Yes, there is. But I...
And
Just for example.
Just as an example. But what an
Yeah.
imagination of an example.
I mean, the shape of this,
The shape.
yeah,
Yes.
is very similar to womb.
I would not say very similar. Maybe similar.
Yeah, and if you put some fish or something alive,
Yes.
yeah, that will, for example, if you put a very young fish.
I'm sorry. I can't continue. This is not related.
Okay.
I see no relationship.
Why a young?
No, you're not wrong. It's just this. I don't see relationship.
Yeah, because I just think if there are some enough pressure in this.
I
place,
think I know what you're thinking about,
yeah,
but it's
yeah.
not like the baby pops out because of pressure. Is that what you're thinking?
Yeah.
You know what?
Uh-huh.
You can ask Colin, the biology teacher. He will give you a much better answer than I could. All I can say is
Mhm.
I'm continuing with the next topic.
Okay.
Okay? So next now. Now it's a word we know from English, but we need to get the precise meaning in physics. By the way, where's August?
He's gonna show up, please.
No, I know this. Does anyone know where he is?
No.
No? Okay. And is that everybody else then? No, we're missing one.
Just August.
Just August.
What happened to you this year? You didn't drink enough
I
coffee.
think so. I only had one cup. It's a serious problem. Right, heat. What's heat?
Increasing the temperature by.
Yeah, if we can get a precise definition of heat. Is that English, Ding Dong?
Yes.
Good.
Ready?
Okay, fine.
Um,
Now look at me, please. Look at me. Let's take an example. A very imaginative example. I know. Here we go. You all know what a train is, don't you?
Tree.
A train.
Oh yes.
I'll draw you one, okay?
I know.
But I need to draw one too.
It's a hammer, not like.
it's like a vase.
Hang on. I didn't say I'd draw you a good train. Roughly. Now, here. Here you have your coal. You know coal?
Yeah.
And here you have your fire.
You mean the black one?
Yes. Okay. And then what happens is they put water in here.
Not water.
Yeah, they put water. And what happens when the water goes by?
A lot of vape.
Becomes turn to steam,
Yeah, it turns to steam.
and the steam in a big column to push the.
Yeah, I think if you look at the old trains, there's this big part in the front, yeah?
Yeah.
I think this is where all the steam is. The steam goes in here. So actually I shouldn't have drawn this here, sorry. This is, should be like here. Yeah. The steam goes in here. And what happens when the steam's in here, Jing Dong?
Go up.
There's lots of steam in here, and then the steam pushes the wheels around,
Yeah.
and then it exits.
Why there in water?
They make the steam. How else do you get steam? You know? Jing Dong, no. You can listen to me, please. So the water goes in, gets hot, turns to steam. The steam is in here, and it gets more and more and more steam. And what happens to the pressure?
Yes, no.
Increases.
Increases.
Bigger and bigger.
Until it starts to make the wheels turn.
Yeah.
And then this is the escape for the steam. Okay?
Yeah.
Now, and the smoke as well from the fire. Now, if you think about it, the train is at rest. So what's its kinetic energy?
Zero.
Zero. And then later the train is moving. So kinetic energy not zero. So where did this energy come from?
From the steam and the.
Yeah, it came from the heat, from the fire. And this gives us the idea of heat. Heat is actually an energy. So the unit is joules. Okay? Heat is an energy and the unit is joules. Now if you think about it another way, what did we say last time about the pressure? We talked about pressure as being like something else.
Equals F over R.
Yeah, but remember I said like the particles hit off the wall.
Yeah, yeah.
When you rise the temperature. You mean this one?
Like this idea. Okay?
It's
So-
nice.
If you put your hand here,
Then a bit warm.
it feels warm.
Yeah.
What you're feeling is the heat energy.
It's hot.
But the heat energy is because of this. Like, look what happens. Let's say this here has 2 joules of energy.
Okay.
It hits the wall and comes back.
So 1 joule.
And maybe its speed, maybe its speed is like 1 joule.
So 1 joule left in the water. Yeah.
So what you feel is 1 joule of heat.
Yes.
It came from the
2 joule.
the 2 joules, yeah.
And release 1 joule.
Yeah. So heat is an energy, and it's the energy from the little particles. And you can relate it to kinetic energy, K. So basically, if you want a formal definition, heat is the transfer of energy from hot to cold. So for example, this one's hot and this one's cold, and if you put them together, energy will leave this one
To
and
the
go
cold
into
one.
this one. Yeah.
Transform TRA.
Transfer, Transfer.
OR.
ER.
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 Mr. Steven,
Yes.
how can we study this one?
Huh?
How can I study? Just memorize the what's it?
Read through the book and see if you remember the definitions. There's questions at the back of the chapter.
Either Stephen.
Yes.
Do you think heat and pressure is the leading of energy?
Yeah, I think most common form of energy for people is heat.
Okay.
Like if you think about it right now,
Mhm.
we get heat from the sun,
Yeah.
we get heat from the heater,
Mhm.
heat from our bodies.
Yeah.
There's heat energy everywhere. Everywhere. I think it's probably most experienced energy.
Yeah.
Mr. Steven?
But I think the heat and the pressure should be 50% and 50%.
Well, there is a relationship between heat and pressure,
Yeah.
and we'll look at that later.
Okay.
But for now, we'll just say heat is a very common form of energy.
Okay.
Yes?
I have a question.
Yes.
Tomorrow after the third you have class or something?
Oh yeah, okay. Tomorrow you have 2 hours of chemistry.
Yeah, and one of them will be math.
One of them will be biology and one of them will be maths. The second one is maths.
Biology, we don't have biology.
Yeah, so you're probably free then, I don't know.
Okay, you are free in that time?
Maybe. Yes?
The pressure causes heat.
Yes, there is a relationship between pressure and heat, yes.
Yeah,
And
first have pressure and then heat.
yeah, let's have a look, okay?
Yeah.
Now,
No, it's not.
no, well, I mean, there is...
Because inside the sun, there are many pressure.
Yeah.
Yeah.
There is a relationship between heat and pressure, but I think you should think about it the other way, that heat makes pressure.
Heat makes pressure.
Yeah, for example,
Uh-huh.
if this gets hot, it means there's more energy, which means they're moving faster, which means they hit the wall harder,
Yeah.
which means there's more pressure because there's more force, because there's more change in momentum. So I would think, Leslie, I think it's better to think
Mhm.
more heat makes more pressure.
At our planet, our Earth, as long as it can stay in the universal,
Mm-hmm.
it's because of pressure. You have pressure so that the Earth can stay.
No, it's about gravitational.
No.
He's correct.
Gravitational force.
What I think the closest thing you're thinking about the sun, okay?
Yeah.
It's very hot, of course, and the heat makes it want to get bigger.
Uh-huh.
But what's pulling it inside?
Mm-hmm.
Gravity,
Yeah.
okay?
Yeah.
So when you look at the sun, heat makes it want to get bigger, but gravity wants to make it get smaller.
Yes.
So they're balanced. Now, what happens when the sun has no fuel left?
No light, no hot, no heat.
No heat. So what happens to this force?
Gonna be smaller
0. So then which one wins?
on the left.
This one here, and then it gets smaller and smaller and smaller and smaller. So when the sun runs out of fuel, it shrinks, becomes a white dwarf.
Even without any fuel, it can move.
Yeah, no fuel, no movement.
This full in the sun, the sun becomes worse
Yeah,
and will die.
well, die. It'll become white.
We're gonna freeze.
Freeze. Yeah.
Stephen,
Yes.
but the gravity is a kind of pressure.
No, but there is, what I'm saying is it's not pressure, but there's a relationship here between gravity and heat, that they're balanced.
Balance.
That the heat makes it get bigger and the gravity makes it get smaller, and the force for the gravity will equal, I suppose you could kind of say like the force from the heat, but it's not quite right here. But anyways, when there's no fuel left, there's no force here, so there's only this force, so it'll shrink. The force goes in. The sun becomes white. Okay? Now, you go ahead, Jack. Now, so how can, there's, to be more precise, the heat inside something is called internal heat. Internal.
Okay.
So, Leslie, like with your bottle here, give us your bottle. Now, this feels quite warm.
Yeah.
You put hot water in it. Whoops. You put hot water in this.
Yeah.
So there's heat inside this. There's energy inside this. This is called internal heat.
Internal heat.
Now, if I was to leave this here, what happens?
Become cold.
Yeah, because this is hot and this is colder, so the energy goes from here to here,
Yes.
or from here to me. That's heat inside is called internal. So please write this word down.
Internally.
Internal heat. Now, how can you change the internal heat? So Leslie,
Yeah.
how would you change the heat for this?
Adding a different temperature.
Yeah, how? How? Give me an example. How would you put more energy inside this?
Put more
Like
energy.
you put more energy.
Yeah, how?
Just pour into hot water.
No, without putting in more water.
Warm it.
Yeah, how?
I think if you want to put more heat
Yes?
By fire.
more energy,
Yeah, yeah. Go on.
you need to make the atmosphere.
Yeah, so like for Leslie's one,
Yeah.
there's the water. So like Mustafa said, you put fire underneath it. You could make the air hotter.
Yeah.
You know, these are all different ways to put it.
Like sauna.
Like sauna, yeah.
Yeah.
So you can put heat inside it.
Even if it was in cold water, put it in the hot water to be
Yeah.
cold.
If you put this into some hot bath of hot water.
Still,
Yeah.
is it possible to heat the water when you put the heater, like water here, that one you draw, and heater here, in a closed place, and you just start the heater, it's heating the room. Is it possible to heat the water?
It's gonna
Yeah,
heat,
the
but
water
not
will
that-
get hotter, yeah.
Not that type of power that will heat if you put it close together.
Of course, but water's temperature will change as
Yeah,
well.
yeah, sure. Well, it depends what the beginning temperature of it was too. Like for example, in your one here, there's the water and there's the heater. So water, heater. Now, if this is very, very hot, it means it'll lose its energy very quickly.
Yeah, it will be warm.
But if this is very, very cold, then the little extra heat from the air will warm it up. So to answer your question, it depends how much energy it had at the beginning. Okay. And this will be related to something called thermal equilibrium, which we'll look at later. Now, we're talking about putting heat inside of something. So here we go. Here's a water. I don't know, milk. And let's say, I don't know, wood. And then let's say
Yes.
metal, let's say iron. Let's say iron, okay. Now, which one do you think can have the most heat inside it?
Iron.
Iron. And which one the least?
Water.
Water. Oh,
Maybe the wood.
Yeah,
Okay.
yeah.
So the idea we have in our head is some things can hold a lot of internal energy, a lot of internal heat. Some things cannot. So the iron, you could probably, for example, have E energy in it. But maybe if you try to put this into the water, it doesn't hold it. So maybe it only holds like E over 2 or something.
How is that?
Because what happens is, if, for example, if you put too much energy into it, it's going to change into steam, for one.
Oh, then we will have questions like this.
What?
Get ready.
Right?
If you will heat the iron and put it in the water.
That's one of the experiments we'll do,
Yeah.
specific heat capacity of
Metal
brass.
can conduct
Uh-huh.
heat.
Yeah, say again, yeah?
Metal can conduct the
Very good. The metal is very good at holding the heat. Now, why is this?
Because
And it's related to what we did last week. Remember with the metal, we had the atoms. And it's like a sea.
Free electrons.
Yes! So because they're free, it's very easy to give them more kinetic energy, which is all heat really is. But if I have something like wood,
But the solid's too tight, I think.
exactly, if I had something like wood, if I tried to put heat into this,
Not
Have
really.
to break the bond
it's hard to break the bond, yeah.
and
Even
have to
the-
remove electrons, so there are not enough electrons to move and conduct the.
Yeah. So we have to be careful now to make sure we get the terms right. But
Okay,
let's say
the metal, the metal.
yeah, there's iron.
Solid, yeah, iron not solid.
It is solid, yeah.
So why it will hold then?
Well, I'm going to talk now. There's iron and stone. Which one will hold more heat?
Stone.
No,
I think maybe stone.
Oh yes, stone. Yes,
yeah.
stone.
You see,
What stone?
the heat is very easy to go into this one because the electrons are free.
No, this is solid, right?
Yes.
And solid's too tight, you say.
Iron. We did it. You said it last time too. The sea of electrons, didn't you?
They have different point, main point.
Yeah, but no, thank you, that's later, yeah. What I'm saying now is, it's very easy to put the energy into the iron, because the electrons are already moving. If I try to put it into the stone, it's more difficult, but it can hold more energy. For example, I'll give you a very simple example. There's 2 electrons, and there's the bond. Okay? And let's say this kinetic energy equals 0. Kinetic energy equals 0. And the bond here, we'll just say bond, B. And then here's free electrons. So if I put in some heat, let's say 10 joules, then what happens to these? They go faster, yes? If I put 10 joules of energy into this one,
Hard to break.
first I will need to break this, and then they'll move.
Oh yes, I know. You mean because of they are bond and we put 10 joules energy to this atom. The first we should break the bond, so we should spend some of the energy, and then the left energy are very small. Just push them a little.
Yes.
minutes.
That is 100% perfect. So what happens is this one here will have less energy, maybe like, for example, 5 joules. So I put 10 joules into both, but which one is moving faster?
10 joule.
This one,
Yeah.
which is like the iron. Right? And this one's like the wood, or the stone. So for example, if I have 10 joules of energy and put it into the iron, I'll feel it's hot. Then I put the same 10 joules into the wood and put my hand on it,
It's
not as hot, because it had to break the bonds. The electrons and atoms, they're not as free.
Yeah.
So this gives us the idea, finally, of what's called
You are right.
specific heat
Yes.
capacity. And the idea is specific heat capacity means the ability to hold heat energy. So, specific heat capacity is a measure of how much energy in the form of heat can be held in volume. Okay. Yes.
Why Asian people they get a fire from
Oh.
from the wood,
Yeah.
yeah, but not iron or stone.
Well, that's slightly different. Yeah, I think it's the friction causes it there. The friction.
Yeah.
So, I guess you don't have to use wood, but that's probably the best thing to do.
Yeah.
I don't know. It's because the friction in the wood.
Friction.
So it's good to start a fire.
Okay.
That's all.
In wall
In a volume.
volume.
Can you?
Yeah.
Can you?
Yes, sure. Before I die, I will. Yes. Specific heat capacity is a measure of how much energy in heat form can be held in a volume. In other words, it's like a battery. If the specific heat capacity is big, what does that mean? Ted, I'm tired of talking. You tell me, what does a big specific heat capacity mean?
This one.
Yeah, if this is big, what does it mean?
It's hold more.
Wait, Ted's
energy.
going to tell me, and then you can say it. Go on, Ted.
It's easy to hold. Much more energy.
Yeah, what type of energy?
Kinetic.
Yeah, kinetic or heat, I think. Yeah.
Okay.
So a big specific heat capacity means it has a lot of ability to hold heat energy.
That the metal without any bonding, it's have high ability to hold the volume.
I
heat,
think there's
right?
actually a table here. Yeah. So if I look at this table, I can see that alcohol has a very high specific heat capacity, and so does wood and probably stone. And metal has a low specific heat capacity. And the reason it has a low specific heat capacity is because there's not strong bonds. Yes. Yeah, come around this way. This way. Now, let's do a formula, okay? Did you write this down?
Yeah.
Yes. Okay, let's do an example. Okay, so wood, stone. Come on.
Okay.
What?
No, nothing.
Iron, stone. And let's make our life easy. Let's say this is mass M, this is mass M, and let's say I put in E energy and I put in E energy. And this makes the temperature change, and this makes the temperature change, okay? But which one will be bigger change in temperature? So,
Excuse
Yes.
me. The big change, you mean the speed of the change?
no, just the size of the change.
Size.
Yeah. Now, okay. So delta T means the change in the temperature. M is the mass, and they use delta Q here, but I don't want to use delta Q. I'll use E. Oh, okay, I'll use delta E. Okay. So this is what happens. Here's your object, and then you put in some energy, and then the temperature changes. This here is the change in temperature, okay? So if it goes from 10 kelvins to 20 kelvins, what's the
10.
10
10.
Kelvin change.
10 Kelvin change. Delta E is how much energy I put in. For example, 10 joules. Kelvin. And then M is the mass.
What happened delta T?
The what?
Delta T.
I'm going to use delta theta only because that's what he uses in the book. But it's the same as temperature, theta temperature, okay?
I'm gonna use theta with a or T, right?
Yeah, theta is temperature T. Okay, now there's a formula, and you think about it logically. You can get the formula. Mass times delta theta times specific heat capacity equals delta E. Yes. Okay. So I'll explain the parts here. This is the mass. This is the change in temperature.
How to spell Kelvin? Thank you.
This is called specific heat capacity, and this is the energy.
Kelvin.
Kelvin, yes. Now I'm saying the formula makes sense, okay? Because if you think about it like this, if I keep this fixed, the mass is fixed, okay? And this, it tells me how much energy I can have inside it. So this is fixed, okay? Fixed. So if I make this bigger, what happens to this?
Small.
No, bigger. And if I make the energy smaller,
That's small.
smaller. So I mean, it makes sense that this is here and this is here. Now let's say I make the mass bigger. Does that mean it can store less or more energy?
More.
More, right? Jing Dong,
Yes.
listen to me.
Oh, yes.
If I make the mass bigger, that means it can have more energy. So if this goes up, this goes up. And if I make it have more specific heat capacity, then it means it can have more energy. So anyways, the formula is correct. So the formula is the energy you put in. Now I use E, but sometimes people use Q. Which do you use?
Q equals
Either is
MC
okay.
delta
E is
Z.
okay?
Yes.
All right. The energy you put in will equal mass
C.
times the change in temperature times specific heat capacity. And just so you know, some people use Q for heat energy.
And T instead of Q.
And some people use T instead of theta. But like, I mean, it doesn't. I don't care.
Just in the handbook they give us like with Q.
Is it? Okay.
Yeah.
So can you do an example?
Yeah, I'll do an example.
T instead of Q, delta Q.
Now, I haven't said what the unit is for C.
Yeah.
So let's see. C equals
Delta Q.
delta Q over M delta T. Delta theta. What is the unit for energy? Joules. Mass,
Kilogram.
kilograms. And temperature?
Kelvin.
So there you go. There's the unit for specific heat capacity. It's joules per kilogram Kelvin. Let's do an example. Here we go. Did you get this formula?
Yeah.
Okay, example. A body of mass half a kg and specific heat capacity C equal to 400 joules per kilogram Kelvin rises from 15 Celsius to 20 Celsius. They want to know what is
It's 15.
The-
This one?
change in heat energy, the Q.
1,000.
55, 600.
So let's use our formula. Our formula is delta Q equals M
C.
delta theta C,
You want the change in what?
temperature, heat. That's a half. What's the 5, isn't it?
Yeah, so it's 2 to
5. And then what's the specific heat capacity? 400.
400.
So that'd be 1,000.
Aren't we supposed to use that 5
Kelvin.
Kelvin
Can use Kelvin.
in Kelvins? Because
Yeah, but like it doesn't, like 15 Celsius to 20 Celsius, the change is 5 Celsius and also 5 Kelvin. Because if I convert this to Kelvin, the difference is still going to be 5.
No.
Yes.
Now, if you want to switch Kelvin, you have to make 273 minus 5. maybe.
I mean like.
Oh, guys! Come on, don't annoy me. I'm sick and I'm tired and I want to go home. Now listen. No, don't touch the calculator. Put the calculator down. Put the calculator down. Look, the formula only asks for the change in temperature. If I convert this to Kelvin, how do I do that? I add 273, yes? And I add 273.
Yeah.
But when I subtract them, those cancel. So it's still going to be 5. Yes, you don't believe me, go check it on your calculator, because...
1000.
No, I'm not even at that.
No, not what I'm saying. I'm saying like at the thing on 5. Like
What?
20
5.
20 minus 15
Yeah.
plus 273. That's what I'm saying.
No, that is wrong. It's only the change in the temperature. The new temperature minus the old temperature.
Okay.
Right?
So it will be 1000 joules.
Yes. So it equals 1000 joules or 1 kilojoule.
Oh. I also can write 1000 joule.
What?
1000 joule.
What about 1000 joules?
The answer.
Yes, I got 1000 joules. You got 1000 joules. The answer in the book is 1000 joules.
Yes.
We're all happy it's 1000 joules, yes?
Yeah.
Great. Now, let's have a look at an experiment. Let's see.
Measuring specific heat from
Yeah, measuring specific heat capacities. Now they do electrical method, which we won't do, and
Right.
methods of mixture, which I think is the one we'll do in the DIT lab. Okay. Uh, okay. Right, let's try and draw this. Now, you won't necessarily do it exactly like this in the lab, but just to give you an idea. Okay, so you have here your boiling water. And you have here your solid. This is the thing you want to measure the specific heat capacity for. So I'll just call it X. And you have here a thread. You all know thread?
No.
A string. Why do I put a string at the end of this?
What's right?
Oh no, Mustafa, don't ask me what a string is. Please. Please. I must have used the word string so many times, you know.
Spring.
No,
It's
string.
a line. It's a line.
String,
It's a
string.
line.
Ah! String.
Relax.
Just like the type of your shoe.
Yes. Why do I put a string on this? Why? Why do you think I would do this?
Because it's boiling water.
Because it's boiling water and you don't want to die. Okay? So you put a string on it so you can take it out. Right?
Yeah.
Great. So that's the start of the experiment. Now, the next part, you put it into some water. Yeah. So later, here is some water. And here is the thermometer, you know, for measuring the temperature. And here is your block here. Okay? And now you basically calculate now how the specific heat capacity. So what happens is, when I take this out of the water, what temperature will this be?
The same temperature.
The same with the water.
Yeah, it'd be 100C.
Mm.
And then I put it into this water, and what happens?
It's gonna be smaller.
It gets smaller, yeah. But what happens to the temperature of the water?
It'll be bigger.
Why it becomes smaller? They are all.
Sorry, you're right. It'll become bigger. You put this into the water, and the water gets hotter,
Oh,
but the block gets cooler.
oh, the upper one is cold water and.
No. This one is boiling water,
Okay.
and you take it out and put it into this.
Okay, I know.
Yes.
Yeah.
So you know that the temperature is 100.
Mm.
Okay. So what happens? The energy from this leaves and goes into
Water.
the water and into what else? The container.
Bottle.
Yes. Now, the name for the container is calorimeter. Actually, copper calorimeter is probably the one. This word here means container. Container. Calorimeter. Anyways, at the beginning of the experiment, what have you got? You've got the mass of the block. Yes? Then you got the mass of the calorimeter. And then you got the mass of the water. You also measure the temperature of the calorimeter. Well, that's easy. That's just going to be the same as the temperature of the water, because they're in the same container. Yes?
Yeah.
And the temperature of the block, what will that be? 100. 100. Okay. So our formula tells me that the energy that leaves this here will be the same as the energy that enters the water and the calorimeter. So if you want to write like this, the change in the energy for the water and the calorimeter will equal the change in the energy of the block.
Like initial final.
Yeah, like that, yeah. That the energy that leaves this will equal what goes into this. Yeah? So they have the formulas here.
Peter Steven.
Yes.
The calorimeter is if I have some fish in my house,
Yes.
you keep the water warm.
Yes.
Okay.
Yes. Calorimeter just means container.
Cutting.
Now, actually, you know what? I should maybe just draw a nice, simple here. So there's the block in the boiling water. And then I put it into the cool water. And then this gets hotter. So I'll call this temperature theta 1. And I'll call this temperature theta 2. Now, which will be bigger, theta 1 or theta 2? Theta 2.
Oh yes.
Yeah, because I take this out and put it in here, and it will be 100 Celsius. Yes? And I put it into this, and it cools down, and it becomes theta 2.
Oh yes.
Yes? So what happens is the energy from the block equals m of the block times the change in the energy for the block times specific heat capacity of the block. And this is what we want to know.
Change in the temperature actually, isn't it?
Plus the C times the.
No, I know. No, I'm just talking about the block right now.
Okay.
If you just look at the block, the energy that comes out of it will equal this.
Mm.
And you're right, this energy will then go into the water and into the other things. Yes?
Yeah.
Okay. So let's calculate. Do you know this? Yes. You want this. Do you know this? Well, not really. You don't know how much energy comes out, so you don't know this. And do you know this? Yes. What will this equal?
Q2 minus
Theta 2. Theta 2 minus 100.
Minus
Yes.
theta 1.
Minus what? Or
Yeah, because this temperature is 100.
Yeah.
It goes in here, it cools down and becomes theta 2.
So why don't we just
Alright, have a think about it. Questions, yes? What's the questions? I'm not finished, but so far, what's the question?
Okay, how can I get the one of them to do the equation?
No, I'm not finished yet. I just want you to understand up to this stage.
Mrs.
Yes.
You go down, please.
Yes, I can.
well, why would you just minus all the temperature of the
No, I'm not. I'm just, if you just looked at the block, look,
yeah.
here's the block. What temperature is it? 100.
Yeah.
I put in the water,
Yeah,
psh,
it
cools down. What's the temperature of it now? theta 2.
Yeah.
Oh, yes, I know.
You know?
I understand.
So, the energy that comes out of this, I'm calculating.
Mm.
That will equal the energy that goes into, what? The water and,
See.
yes? Right?
Yeah.
Right. So what happens to the water and the copper calorimeter?
They get
So, water plus calorimeter. So again, the formula. It's the mass of the water times the change in its temperature times the specific heat capacity of water
Yeah.
plus the mass of the container times the change in its temperature times the, that's a W, specific heat capacity of the container. Now, two of these things will be the same. What two things will be the same?
Temperature.
Temperature change is the same. The temperature for the water and the container is the same. So I can simplify this into change in temperature of the water times MWCW plus MC CC.
See.
So this energy will go into this. The energy that leaves the block will go into heating up the water and the calorimeter. So that means this equals this. Yes?
Mm.
So I have now delta theta W MWCW plus MCCC equals MX theta there and CX equals MX delta theta X and CX. Now we can simplify this more. I'll just write dot dot dot. What is this one here? The change in the temperature.
100 minus.
No, but this
Yes.
is 2 minus 100.
Dollar 2 minus 100.
Yeah.
What would it be?
There are 2 minus 100.
32.
Theta 2.
See that?
The temp. Very good. The temperature here minus 100. Now I have to be very careful with my signs here. One would be negative, one would be positive. You know, I have to be careful. I would like to keep the equation on the left positive and the one on the right positive. So it'll get cooler. So I think I should do it as 100 minus
See that
theta
too?
2.
Yeah.
Okay. And this is theta W here. So what I'll do is, I'm looking for, oh sorry, here's my CX at the end. Because I'm looking for CX, I'll rewrite this as CX equals delta theta W. What was in here? MW CW plus MC CC all over 100 minus theta 2. Okay.
Where is the MX?
Yeah, where is MX?
Yeah.
Here it is. Okay. Now, do you know the change in the water temperature? Yes, you do. Because there's the water there. It's theta 1. Before I put it in, sorry. And here is theta 2. So it'll be, the change will be, will it get hotter or colder? It'll get hotter, so I do theta 2 minus theta 1. So I get Cx equals theta 2 before I put, or after I put the block in, minus theta 1 before I put the block in, all over 100 minus theta 2 times mx. And then here, mw, cw plus mc, cc. Now, you know this. You measured this on your thermometer. You know this. You measure this. You measure this. You measure this. You measure this. And you can know these beforehand. You can look it up. Okay? The specific heat capacity of water and specific heat capacity of the material, the copper maybe. You can look it up. So you can use this to calculate Cx. And you do the experiment a few times and take the average to be more accurate. Like, remember with the pendulum, how many times did I swing the pendulum? 10. And then I divide by
2.
10.
I think. Yeah.
Yes?
Yeah.
Okay.
Can we write?
Yes. Now, yes. Go ahead.
Can you go up?
Oh.
What is the Q2 minus Q1? I mean the theta 2 minus theta 1.
That's the change in the temperature from before you put the block in and then after you put the block in.
So it's big minus small. It's small minus big.
I want to do the bigger temperature minus the smaller temperature so I don't have negative signs.
So theta 2 is smaller than
No, theta 2 is bigger because you put the hot block in and you make it warmer.
I mean the top theta.
Theta 2 is bigger than theta 1, yeah.
And can you go up to right?
Go up. How far up?
Why do you change in temperature to Q2 minus Q1?
Q2 minus Q1? Where do
I
I...
mean theta 2 minus theta 1.
That's the change in temperature.
Because it raises
Yeah, go. You explain. I'm tired. You explain.
the temperature goes up.
Yes.
Compared to
So temperature.
Go up.
yes, the theta1 is cold water and the theta2 is
come
hot
down.
water.
Yeah. Up.
Because of the hot box put into the water, it let the water temperature goes up.
Now, just to finish, please, with this. Of course, I put the block in the boiling water. Yes?
Yeah.
And the reason I put it in the boiling water is to make it very hot. Now, if I don't leave the block in long enough, what happens?
Pardon?
If I don't leave the block in long enough in the hot water, the boiling water, what happens?
Don't get the temperature that you want.
Yeah, exactly. So I think what you should do, we said we put it in the water to make it 100. Yes?
Mm.
But maybe it doesn't become 100. Maybe it's nearly 100. Or maybe it's more than 100. So you should also, if you want, you should take the temperature when you take it out very quickly.
Mm.
So rather than saying 100 here, we can just make another theta called theta 3. And that's the temperature when it comes out of the boiling water. And I would hope that this should be
100.
nearly 100. But maybe it's not. So if you want to be more accurate, you can modify your equation to have this theta 3 in it. Less errors is always better. But I think that if you put it in the boiling water and if you leave it long enough, it should be 100. But it might be more than 100. Why?
More than
Because
100.
the heat of the
Yes?
substance as well, also.
The steam.
Yeah.
Look here. Here's the block. Here's the water. You know, there's steam here.
Oh, yes, I know.
You know, like maybe when I take it out.
The steam hit the wall, hit the block.
Yeah, Or maybe when I take it out, you know, you want to pick something that loses its heat very quickly. Because if this is very hot and I take it out and it gets very cold, you know, it's less accurate.
And I think there are another situation. You put the block under the bottom, and under the bottom is the fair, and the block and the fair are close, getting very closer.
Yeah. Yes. Yeah. You're right. So I mean, this is what I would imagine if you want to do it perfectly. You have your hot water, and you boil the water, and you put the thermometer into the water,
Middle.
and in the middle, and you fix it so that the temperature is exactly 100, and then you take the thermometer out and put the block in. But will you get it at exactly 100?
No.
No. So this is why I put in the theta tray, to be more accurate. But the idea is you try to make it nearly 100.
So theta B is nearly 100.
Yeah. I think for the experiment in January, we'll use brass.
Brass?
Brass, yeah. We'll use brass.
Can we do an example?
No, I don't. Example of this? Well, it's in the book for you to read if you want. Yes. What? Theta 3 is the temperature which should be roughly 100 degrees of the block in the boiling water. Theta 1 is the temperature of the water before you put the block in. And theta 2 is the temperature when you put after the block goes in. Yeah. Right.
What's wrong with the brass?
What's wrong with brass?
Yeah.
Brass is a material.
Yes, sir.
We'll use brass to measure the specific heat capacity of brass.
Oh.
Okay. Right, that's heat. Now, I actually won't do Newton's law of cooling because I don't think it's on the course. I will do, however, now latent heat. 68. Now, latent heat. Let me explain this. Look carefully, please. Here is ice. Yes? Temperature -1 Celsius. Here is ice. Temperature 0 Celsius. Here is ice. Or maybe I'll say water now. Temperature 0 Celsius, roughly. This is my idea, okay? Here's my ice. If I put energy into this, I'll make it get hotter and it will turn into temperature 0. Yes? If I put more energy into this, I think it will get hotter again.
Yeah.
But it doesn't get hotter. Instead, it changes into water.
Yes, liquid.
Yes. You need energy to change the form. This is called latent heat. So, for example, water. No, look here. Look here. Ice, 0 Celsius. Water,
0 Celsius.
0 Celsius. I put energy into this, it changes it into this. Is the temperature any different?
No.
Yeah.
No change in temperature. So where did my energy go? My energy went into changing the structure from ice to water. Solid to liquid. Yes. This is called latent heat or latent energy. It's the energy you require to change the state, solid, liquid, gas. Okay? Let me do an example for you with the water and the ice. No, I'm going to do it again, but with numbers. So here is the ice, and let's say its temperature is θ1, and here is the water, and let's say its temperature is θ2, and I put into this delta Q, and it makes it go into water. So, the energy, the change, excuse me, this holds energy, and the energy will be held in the water also, but it will lose energy because it has to change its form. So mass of water times temperature, ice, but it's still water, water, specific heat capacity of water. That's how much energy can be held here. And this actually will be θ1. And how much energy does this hold?
1.
Mass, water, θ2, this one here. This is how much energy is here.
1.
This is how much energy is here.
They should be equal.
Will they be equal? I don't think so. I think you need a plus
This
L.
What's
Plus L.
Yeah.
Why?
This is the okay. Hang on, let's start again.
They are the same mass and the same temperature and the same color.
Yeah. Okay. I understand. No problem. Let me explain again. I'll explain more clearly. This is. I'll get rid of this. Okay. Forget it. Ice. Water. You're right, Jingdong. The energy here will equal the energy here. The energy here will be mass times θ1 times C.
Yeah.
And that will equal
Same.
mass times θ2 times C. True. That is true. Now, if I come along and add energy to this, I call it delta Q. I put more energy here, which means there's more energy than this one here.
Same thing.
Okay, the same. The energy will be in what form? It'll be held in this, but also because it changed the form. So for example, this is the energy in the water. This is the energy in the ice, but I also need the energy to change the form. Okay, so I need something to demonstrate it here. Okay. Right. This is the ice. It has energy. I come along and put energy into this. It makes it hotter. But then it also changes the form. So if I calculate how much energy is in this and say it equals how much energy is in this, will I get the same? Will they be equal?
No.
No, because there's also the energy because it changed the form. So the energy in the water will equal the energy in the ice plus the energy required to change the ice into water. So that's why I had plus L here. You seem confused, Jingdong.
Maybe from the graph it will be more clear. Like,
From the graph, yes, but
I mean that's the energy that changed the shape from ice to
Yeah.
water.
Okay, one more time for fun. Here is the ice, and I can use this formula to calculate the energy in the ice.
Yeah.
And then this is the water, and I can use this formula to calculate the energy in the water.
Yeah.
Will they be equal?
Yeah.
No. No, because this only tells me the energy it holds in heat form. It doesn't tell me the energy that's held in the changing of the form. This formula here just tells me the energy it has because of its temperature. It does not tell me the energy it has because of its form.
Also, I know.
Go ahead, I'm tired of talking, go ahead.
L means the energy which expand in changing the shape.
That's it.
Is right?
Yes. Okay. And this is called. What did I say it's called?
And if we don't.
No, what's the name of L? Latent heat. Latent heat. Yes, and go on, Jingdong.
And if we don't consider the shape of the change of the shape, they should left equal right.
Yes, exactly. If there was no change in form, this would be 0, and this would be true.
And that tells us if the material's shape will be changed, there
Yeah.
also should be energy spent.
Yeah. If the material changes shape, some energy will be spent to change the shape and will not go into the temperature. Yes. That is called latent heat. Latent heat is the energy, where is it
For
going?
to change the shape from.
The heat the body absorbs and melts and evaporates, this is called latent heat. So you have
Latent heat, not latent heat.
latent heat.
Heat, okay.
Now you have latent heat for vaporization and then fusion as well, isn't it? Yeah. So, Jingdong, this vaporization, this is how much energy you need to go from a solid to a gas. The energy to change from solid to gas.
Very more. Very much.
Probably very much. And then fusion, what do you think fusion is?
Water?
Gas
Yeah.
to solid is not.
Yeah.
No, a liquid to solid, I think.
The complex of liquid and solid.
Yes. Yeah, latent heat diffusion. Here it is here. Yes, this solidifying. So when you have a liquid and it changes into, it freezes. That's fusion, latent heat of fusion. So fusion means the energy required to change it from liquid to solid, and then vaporization is the energy required to change it from liquid to gas.
Vibration from liquid to gas?
Yeah.
There's no gas to liquid.
Gas to liquid? Yeah, there's actually some interesting
Yes,
ones.
yes.
Let's have a look.
Aye.
Wait.
Can be just liquid.
Wait. Liquid, solid, gas. So, everybody look please. Look, please, look.
Okay.
Liquid to gas. How do you do that?
Fusion.
Heat.
To,
Boil water, for example.
liquid to gas? Ah, okay, yeah.
Okay.
This is vibration.
Liquid to solid.
Liquid.
Release
Like-
energy.
Freeze ice.
Okay, Mr. Steven, just a minute.
Yes.
On the right is vibration, right? Latent heat vibration.
Here,
Yeah.
this is liquid to
from
gas.
liquid to
This is vaporization. Yeah. And liquid
to
solid is
is
fusion.
latent heat fusion.
Yes.
Okay.
Now,
And there must be something from gas to.
yeah, that's what I'm trying to do with this. Okay. Now, solid to gas. Does anybody know this?
Yeah.
Yes.
Aye.
Yes. I.
Elements.
No, I want an example of something that goes from solid to gas.
In the morning, it's very cold. You can see many wines
No.
on the.
Dry ice. Does anybody know dry ice?
Yeah. Made of CO2.
Very good. You take CO2, you put it in the fridge, and you freeze it into ice. So you have CO2 ice. If I put the CO2 ice on the table, it does not go into liquid form. It melts straight into gas form.
So steam will come out of it.
Yeah, it looks, yeah. So do you ever see on movies, you know, when they have experiments and people are pouring stuff and all the steam comes out? It's probably just dry ice. You know it?
Yeah, you mentioned the Chinese wedding.
Chinese weddings?
Yeah.
Are you sure?
When the
Do you use dry ice in Chinese weddings?
Wedding.
Yeah, Yeah,
It's men
That's
and
Arabic wedding.
It's
They don't do that.
men and women they are getting married.
Yes, that's a wedding.
Yes, sometimes.
You use dry ice?
Yes.
Really?
Yes.
Yeah.
For what?
Yeah, for what?
To
To make an iced tea?
to celebrate to decorate the marriage.
Oh, do you like make a shape out of it? Like the
Yeah,
swan or
To,
something?
to make the atmosphere more exciting.
Okay, whatever. That sounds great. That sounds great.
It just makes the wedding become more romantic. That's all.
Very romantic.
Instead it is something in the toilet, like a ball. The men's toilet. Men's toilet.
Oh,
There's a ball in
yeah. No, are you saying from solid to gas?
it. Yes.
I don't know actually. I think it still goes solid liquid.
No, it's not like.
Okay. So what Ted is talking about is in the men's bathroom. It's blue. Yes. Are you talking about this thing?
Yes.
Yes. Solid to gas. I don't know. I don't know. We can look up on the internet and see what we can get. I wouldn't have thought so, but maybe. Okay. I should also do some graphs with you. Okay. Right. Okay, I'll do this next part a little bit quick. So, did you write this down? Oh, well, it doesn't matter. I'm going to a new page. Okay, linear expansion. So, Leslie, you should know what the word expansion means now. What does expansion mean?
Expansion is, for example, x plus.
Oh, that's maths expansion. No, physics expansion. What does that mean? It means to get bigger.
Yeah.
So what do you think linear expansion is?
Linear is like a like.
Straight line. So look, picture this. I have here.
Yeah.
If I make this hotter, get bigger or smaller?
Huh?
If I make this hotter, does it get bigger or smaller?
Bigger.
Bigger. Now, because it's a straight line, you call it linear expansion because it only expands this way.
Yes.
Yeah, in telephone.
In one distance, it can be change the shape only in one distance.
Correct. This is called linear expansion.
If we hand in hand.
Huh?
Hand in hand.
Hand in hand?
Yeah.
What are you talking about?
I mean, if two people they stand on the straight line
Yes.
and they hand in hand and like this.
I don't know, Leslie, you're being very romantic today. I don't know.
Just shut up.
No, it's nice, but I don't see the connection here.
Yeah, nice. No girls here. We are just 8 testosterone. No.
There's no-
It just means there are big line and
All right. Okay.
it doesn't matter.
No. Nobody talk now. Your teacher's getting too tired. Look, linear expansion. I give you a good example, okay? You see the telephone, the electricity pylons, and you have the cables. Okay? When it gets hot, they get bigger. So they hang down a bit more.
Yeah.
And when it gets cold, they get smaller. So it gets
Well,
tighter.
we did now from the cable to.
Yeah. So if this got hotter, it would hang down more.
Yeah.
This is called linear expansion. Okay? And there's a
What's written here then?
this alpha here is equal to the change in the length over the change in the temperature times 1 over the length. So for example, if my cable gets 1 centimeter longer, or like this, because I increased the temperature by 5 degrees, and let's say the original length was 10 meters.
10 meters old length.
Old length.
Okay.
Change in length, change in temperature. So let me calculate this. Can you calculate, please? That would be 0.01 over 50. That would be 2.
It's 0.0002, I guess.
Don't. This is.
I know, they have calculators.
Your math team.
2 times 10 minus 4.
Minus 4.
Yeah, I was right.
Now, let's suppose that it's 10 meters, I heat it by 5 degrees, but it gets 4 centimeters bigger. Please calculate now. Well, it should just be 8 here, shouldn't it?
Yeah.
Yes? So look, you can rewrite this formula. But anyways, this here tells me if it's big, it means what, do you think? It's very quickly, easy to change its length.
Yeah, that means there are big change in temperature.
Yeah. So give me something that has big alpha. Maybe copper, something like this. And what about small alpha? Maybe, stone. No, I need to think of a cable, a wire.
No,
Huh?
light,
Plastic.
Plastic?
no, light, and the iron
Oh, okay. That's big or small?
thing.
Big.
Small.
Small, maybe.
Small. If it's big.
But if it was big, the light bulb would explode.
Yes.
Yeah. That's a good example for small, maybe, I think. Anyways, look, you can rewrite this if you want. You could also say, look here, delta L equals delta theta times alpha times L. If I just bring these two up here. So in other words, my point is this. If you know the change in temperature, and if you know the original length, and if you know the alpha, you can know how much bigger it gets. But this is the formula.
This is for alpha.
This is to calculate the alpha constant. How easy it is to change the shape. Right, you just need this, okay? Next one now.
Big area.
And then it would be area, of course. Which is, here it is. Beta, which is the change in area over the change in temperature times 1 over the area.
Same thing but change to area.
Mr. Stephen, can you go up for just 2 seconds? Yes, sure.
Look, all I'm thinking now is,
Okay.
in about 25 minutes or so, I'm going home. I'm going to have some coffee. Going to go on the bus. Use my laptop. Going to relax. That's what I'm thinking about right now.
Rush hour.
I'll read. Okay. This is if it's area. So like the book. If I make this hot, it'll get bigger.
Yeah.
And again, I can measure and calculate the beta. And it's the same meaning. It's the ability to change its shape with temperature. And then, of course, you don't even have to look at the book now. You can guess what the one is for volume. So what letter do you think I use for volume?
Gamma.
Alpha, beta, gamma equals delta
Volume.
volume over No, you don't need to look at the book. You can work it out.
That the temperature multiplied 1 over volume.
It's all the same.
For what?
They are all equal. Just that they.
No. These are for different shapes. So if I have a cable, I need alpha. If I have a flat page, I need beta. And if I have a volume, I need gamma. Okay. I lost my page now.
271. You have to memorize this formula.
Yeah, but they're not even difficult to remember because they're all the same. The same form, yeah. Okay, next now. Thermal stress.
Yeah, why we didn't take that one?
Which one?
Version of solid. No, because we take page 69.
I think it's too detailed, this book.
It is,
Last 5 years, I saw last 5 years exam, I never seen those kind of formulas used.
I know, that's why you probably won't see them again, but it's good for your general education. You're all going to be engineers next year, yes?
It's not part of our
No, Mr. Stephen, why is 69 see bonding energy of latent heat? Why you didn't get that?
Because if I did everything in the book, we would all die. So I need to decide what things to cut out. Not everything's going to be on the exam. So I'm doing, like in maths class, I try to cover everything that's on the syllabus plus a little extra for
What's
good
the-
luck.
This is the little extra?
This is the little extra. Okay.
So this is
Right. Next now.
It will, no? It's a little extra.
Come on. Next one now. Let's see. I think we might look at thermal stress now, if it's not too complicated for you.
How about the break?
No. I'm sick, and if I don't need a break, you, as a young individual who's not sick, definitely does not need a break.
have 10 minutes left.
A little bit more. I have stuff to cover still. Okay, do you remember back with Young's modulus?
Yeah.
Yeah.
What's Young's?
Stress over strain.
Stress.
Over.
Oh my goodness,
Yeah.
I'm getting tired. Yeah, I know. It's getting to that time of the day. Stress over strain. And there was also a formula for Young's modulus for energy.
O2
That's
multiplied by
half. Okay.
Stress
Over strain.
multiply strain. Which he also has here.
there's no V. There's no.
No, there's no V in it. You realise that was the exact same question Mustafa asked last time we did this, and you gave him a hard time for asking if there was a V in it. So I just thought, for the record, I should point that out, so you should be more humble in future with other students' questions.
No.
No, that was exactly, he asked me the exact same thing you just did, except you gave him a hard time about it, and he didn't say anything to you about it now.
Yeah.
Yes?
Because he didn't understand what's going on.
No, because he's a nice guy.
Alright, I'm not a nice guy.
You admit it? This will make my life so much easier now that you've accepted it. Right. Continuing now with Young's modulus. Energy is a half stress by strain. Come on, let's concentrate. We're nearly finished now. So if you look here,
We take this from the.
I know, but I'm looking here. No. Oh, the one with the volume, yeah. Actually, you know what?
No, don't talk about it. If you don't think it's
I'm not going to. I don't think we need to discuss this right now.
Wow.
Instead, what I want to do, a very, very, very short example of something. Here is our ball,
Okay.
1 kg. Here's the wall.
Okay.
Do you remember E equals a half? What does this mean? So this has speed of 10 meters per second. It hits the wall, it comes back out with speed of what? 5 meters a second.
Yeah, kinetic energy.
Kinetic energy. Yes? So what was the energy beforehand? A half v squared. And after? A half m 5 squared. So before is 50 joules and afterwards is 25 over 2, 12.5 joules. So how much was lost?
50 minus 25.
Yeah, 37.5 joules. Okay?
37.5.
Now remember, we had a formula called efficiency. That was the energy out over the energy in. Remember this? So that is 12.5 over 50 multiply 100. What does that equal? 25%. So this means that 25% of the energy is saved and how much is lost? 75%.
And how did you get 37.5?
This minus this.
Oh,
Now, question. Where did this 37.5 joules go?
What's
raised to the
to
wall on the ground.
Heat.
Oh yeah.
It hit the wall and went off, and now this is a little hotter.
Yeah, and the wall.
And the wall's a little hotter. But just to make our life easy, let's just say the ball is a little hotter. What's the new temperature? Let's say, for example, the temperature of the ball was 20 Celsius. And we want to know what the new temperature is. Okay? So we can use our formula. The change in heat energy will equal MC change in temperature.
So we don't know the C.
No, but let's pretend it was something that we did know. So I'll pick something in the book. We need something that kind of, rubber, perfect. You all know rubber?
Yeah.
You want to know the second?
Rubber C equals 1.7 times 10 to the 3. That's how much specific heat capacity is in rubber. You all know rubber, yes? Rubber ball. Okay. So you have 37.5 equals M C, and then you want the delta T here. M is 1. So calculator please, 37.5 over 1.7 times 10 to the 3. 0.022. So if the temperature beforehand was 20 Celsius, what is it now?
So you will make it 0.02 minus that.
No, plus. Increase the temperature.
Wait, delta E equals T2 minus.
No, delta E just means the change in energy. It's going to get hotter, so just add it on. No, don't think of it like this. You'll confuse yourself. Okay, whatever. So look, I have my rubber ball. I throw it against the wall. It comes back. It's a little hotter now.
So T2 equals 20.02.
Yeah. It comes back a little hotter. 20.02 hotter is the new temperature. Yes? No. I'll take as long as I need. Don't worry, it's recorded. You won't miss anything. Okay. The reason I did this example for you is, this is important. The reason I did this example for you is because in the exam, this is a good question to ask you. Remember we did the ball hitting against the wall and it loses energy, or the pendulum and it loses energy. For example, in the exam, it'll be like A, B, C, you know, how fast, what's the new speed, blah, 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 A, B, C, and then the last part, D, would be something like, please calculate the new temperature in the ball because it lost energy. So they like to mix this into other problems to make things more practical. Okay?
Can you go down, please? Can you go up, please?
So you can do anything you want. Here?
Yes, it's here.
That's 10 to the power of 3.
Oh no, sorry. I think we should go up, please. Again.
How far now? More?
Yes, it's here.
So I'm trying to think of an example now.
And how do you get 50 and 15 G?
Huh?
How did you get 50?
A half multiply 1 multiply 10 squared.
Can you give me the formula?
Of course I can.
Half and this guy.
Yeah, oh, where's my
I think I
pen?
missed this
How
class.
about you did, Jing Dong, you missed this class. This is the formula for kinetic energy.
Oh.
Your KE, yes, I think you saw this already.
Oh, yes.
Yes? Okay.
And the KE should be equal the E is also energy.
What?
The KE means energy.
Yes.
It also should be equal the E we started today.
Related, yes.
What's this called, this even that we did now?
Thermal physics. Oh, what we just did?
Yeah.
No, this is just me doing an example of using specific heat capacity. Okay. So, I don't have it, but like, you could do it for... Ted, your calculator, please.
Yes.
Per day, humans need 2,500 kilocalories, which equals 2,500 or 2.5 million calories. Ted, please multiply this by 4.2.
Why?
To make it joules.
Yes.
What is it?
105 105
Multiply by 4.
1 2 3 4 5 6 7.
1, 2, 3, 4, 5, 6.
1.5 times 10.
Oh, 1.5 times 10, 7. Yes? Are you sure?
Yes.
Alright. That's how much energy a person needs per day.
But it can get some coffee.
Maybe 6.
Oh, come on. Can,
105.
what is it, Albert? 1.5,
10.
105.
Yes, I said 10. Sorry.
That's okay, Ted. You're trying. 105000000. Yes?
Yeah.
That's how much energy you need per day. Now, let me give you an example. What's normal body temperature?
37.
Is it
Yeah,
that?
yeah.
6.5.
No, 36 not good, the other 7.
27.
36.5.
Yeah.
36.5.
Yeah.
I know.
Is that body temperature?
Yeah.
Yeah.
36.5.
Yeah.
Run to 70, to 37.
It was 7, yeah.
Wow.
Between these.
I didn't know.
Between,
I-
yeah.
Alright, whatever.
It's an example. It's just an example.
No,
Okay, just,
it's roughly 37. Is it that high?
Yeah.
Less.
You never get sick.
How many days have I missed so far since starting? Huh?
Roughly 36.
Okay, it doesn't matter. Whatever. We'll say 37.
Yeah.
So here you are, 37 Celsius. But let's say the room is 36 Celsius. Okay? And you want to be 37 Celsius. So what happens? You need to increase your temperature. So let's calculate how much energy you need to do this. So delta Q equals MC delta theta. Now the delta theta is easy because you just want to increase it
Yeah, there's
1
no way
degrees. Yes? So the energy will just equal the mass times the specific heat capacity. Now, Jingdong, I'll pick you because I don't know, maybe you know. How heavy are you? What's your mass? kg?
Nice.
Yeah, kg, yeah. Don't be shy. We're all men here. What is it?
86.
Okay, delta theta for Jingdong. Yes, announcement.
I need to give this to Leslie.
Okay. Will I just hand it to him at the end,
Yeah.
or do you need feedback to me?
No, the feedback is there. Well done.
Okay.
Thank you then.
Okay. Right, so delta theta for Jingdong will be, what did you say your mass was?
86.
86.
86. Times specific heat capacity of Jingdong. Now what's Jingdong made out of?
What?
Flesh and bone.
Flesh and blood. Yeah, he's mostly water, right? But there's a little bit of carbon and other stuff.
So what's delta Q?
So what's specific heat capacity of water? It should be here. And Bowens, I know, and other stuff, but
Okay,
with,
Mr. Stephen?
wait. I'm looking for specific heat capacity.
Interesting.
Yes, so, wait. The specific, yes, Leslie.
Yeah, I think 86, maybe 19 or
Right, you know what? For the temperature,
yeah.
I don't care. All I care is I want to make the person 1 degree hotter. So if it's 36, I'm going to make him 37. If it's 1,000,000, I'm going to make it 1,000,001. That's all I care about. Now, the specific heat capacity of water is, where's it gone? 4.2 times, no, don't, wait, 10 to the 3. But this is for water. And we said Jingdong is not just made out of water, he also has some bones and hair and other things. Do you think bones has higher or lower specific heat capacity? Higher. So let's say make Jingdong 5. We all make it 5, okay? All right. Can you calculate this, please, Jingdong?
5 times
So guess what?
It's 42.
This is how much energy is Jingdong requires.
4.3 times 10, 1, 2, 3, 4, 5.
Wait, did you put the 86?
Yes.
And 5?
4.3
Yeah.
times 1, 2, 3, 4, 5, 10, 5.
Well, I want the full number. So what's it? 4?
3, 4,
43,0000.
yeah.
That's how much energy Jingdong needs to increase his temperature 1 degree. But how much energy does he need per day? You see, he needs this much per day. He needs 10.5 so let's just say he needs 10 million joules, and this is roughly half a million.
So the delta
Joules.
Q is 9.
No, so all I'm saying is to increase your body by 1 degree, you need a lot of energy to do this. You know? This here, let's see. Jingdong, what did you have for breakfast?
Come on, we're gonna calculate
Nothing.
the day.
Nothing. Maybe a cup of
Your parents will be very angry at you. No breakfast, just coffee.
Yes,
What did you have for lunch?
a chicken roll.
Good. So a chicken roll, I think
500
about 500 calorie. So about 1/5, about 2 million joules. Would it be? I think so. So I say, Jing Dong, your chicken sandwich probably had about 2 million joules. So 1/4 of your chicken sandwich, the energy was used to increase your temperature by 1 degree.
Yeah.
Okay? Now, the point I'm trying to make here is, in the exam, they like to do these little questions where they try to make it practical. You know what I mean? Practical?
Like
Real life.
Real life?
Yeah, real life. You know real life?
real life.
Not clear.
Yeah, I know.
Explain it to them.
What's that?
Real life. You mean real life?
Yeah,
Life.
yes,
L-I-F-E.
yes,
But when you add a real,
I-E-A-L.
yes.
what's the difference real life and life?
Uh-huh. There's no difference actually, you're right. It's the same.
Yeah.
So what I mean is they try to make a problem for day-to-day life.
Oh, it's your common life. Just-
Yes!
Just today you do, every day you do the same thing.
Yes,
Like-
that's right. So this is a realistic example. So my point is, today maybe you need 10 million joules, but if it's very, very, very cold, you could need 50 million.
Oh yes, I know.
Very hot.
Very hot.
Yeah, you still need more.
Now that's very interesting if it's very hot, because you have too much, you want to lose energy.
Yes.
So
You eat less.
you should eat less.
Less.
Yes, you need less. You know the people that go to the North Pole?
Yeah.
You know the North Pole?
No.
Oh my goodness. North, South.
Oh yes, I know.
Santa Claus lives here.
It's cold.
It's very cold. Now, here in Ireland, maybe you need 2,500. But once you go here, you could need 10,000 or 20,000. Or even, I think I've heard of people needing 40,000.
Yes.
Because your body needs to use so much energy to
make it
increase
grow.
the temperature. So, what have we learned today? Heat is just a form of energy. You can see it in temperature. You require temperature, energy to change the form from solid, liquid, gas. We did specific heat capacity. We did different types of thermometers. And we also looked at an experiment to calculate specific heat capacity of brass. I didn't do any graphs, except for one actually. But, you know, the type of graphs, look here please. This is the last thing I'll do, okay? Temperature, energy. Temperature.
Both will increase.
And here is 0. I'll use Celsius. So when the water is very cold, it's ice. Yes? And then I increase it, I put in more energy. So no energy, it's ice. And I put in more energy,
Gonna be.
it gets warmer.
gonna
Oh,
be
sorry, it's frozen. Let's say -10. I put in more energy,
0.
and it gets warmer, warmer, warmer. And then what happens when it gets to 0? Look closely.
Water. Liquid.
It doesn't increase its temperature because it changes into liquid. And then it goes up again. And then what happens when it gets to 100?
It's gonna change to the.
Then its temperature doesn't change,
Let's change the material to the gas.
but then change the gas. So this part here on the graph is because there's no temperature change, and that's because it changed its form. So again, this is latent heat.
So when you put the temperature, they are equal. But if you look at energy, they are not equal.
Exactly right, exactly right. If you look at 0 degrees water and 0 degrees ice, there is no difference in the temperature, but the energy is quite different.
So that's the reason you put L.
So L is accounting for the difference in temperature, energy, heat energy. Yes,
To the advanced.
you want to stand. Then it's fine.
Okay.
Right. You have questions at the end of this chapter. You also...
Oh,
Wait, no, wait, later. Do you all have this still? Look here, look at your teacher. Do you all have this?
Yeah.
The questions for today are on the next page. Please do it for homework. If you don't do it for homework, you won't remember, you won't learn, you won't get a good grade, and you will be in Emer's office crying. And I will be outside the office laughing.
All very logical.
All very logical, you're right, Ted. Okay, look, we'll finish there, and we're going to continue with the thermal physics next week.
No, tomorrow.
No, we didn't have it. So.
No, we have an extra maths class tomorrow.
Oh,
Yes, you all have chemistry tomorrow. First hour, biology. Second hour, maths class with me. There you go, Leslie.
Thank you.
Oh, no problem. My pleasure.